this is where I left the thing last time on the bit axis. So previously we were talking about byte axis. That is, the word size is a byte. So all of these instructions before, they were operating on a byte at a time. Maybe you have an address that's 16 bits, so that might be another possible data size. But here, these are for bit level manipulation. And so now in 8051, remember there's A for accumulator. There's also something B, which is another a byte register. Now C is called carry. Now unlike A and B, which are 8 bits, C is only 1 bit. It's actually part of a byte. And this bit goes by the name of either C or CY. Okay, so CY stands for carry. That's the first letter and last letter of carry. Um, Now you'll see the difference between the two. There are two different names for the same thing, and C is implicitly addressed in that it's part of an instruction, so that the instruction requires C to be used, and so it's not explicitly represented. Whereas if it's CY, then just like A versus ACC, right? ACC means it's explicitly addressed like a special function register. Here, CY is an explicitly addressed bit. That's part of this bit addressable space. You'll see the contrast in a little bit too. Now, 8051 is one of the few architectures that supports what's called a bit addressable region. That is, there's one part of its on-chip or CPU on-chip memory that allows you to name every single bit. Each bit has its own address. That's actually pretty unique among microcontrollers or microprocessors in general. Many are limited to just byte addressing. So the smallest unit you can access is usually a byte on most processors. Now, 8051 allows you to name individual bits. In other words, there's a chunk of memory that can be named at the bit level. Okay, and so this is part of iData and part of and then of course, as you remember, iData includes the special function register region. Okay, and these are the instructions that allows you to do bit level manipulation. So they're set bit, clear bit, move, or one version of move involving a bit address, CPL for complement, ANL for AND, logical, ORL or logical, and then there's I guess XRL doesn't work at bit level. There's JC, JNC, JB, JNB. That's to take a jump or not to take a jump if the specified bit is set or not set. Okay, C is for carry, B is the bit address. Okay. Now, bit addressing mode essentially says when you specify an instruction with its operands, the operand actually specifies the location of a bit or something like that. And the bit is specified using like an 8-bit address. Okay, so now 8051 has this overlap between bit addressable region and parts of its iData memory. So as you recall, iData has it's this 256 byte space, right? The first 128 bytes are overlapping with its registers and the default stack space, and then anything from 128 up to 255 or hex 80 up to FF. That's part of the special function register space. Now, not the entire space is bit addressable, but parts of it is bit addressable. Which parts? So 8051 address from hex 20, which is decimal 32, for up to, I guess, 16 bytes after that, so 2F. Right? So that part of the memory space of iData is bit addressable. And then special function registers the byte 80 hex, 88 hex, 90 hex, 98 hex, A0, A8, B0, B8, and so forth to F0, F8. Those are the bit addressable bytes. Does sound confusing? Well, a little bit. Okay, now let's divide these into two regions. Okay, the first region, as I was saying, overlaps with the address 20 to F, right? So those are 16 bytes. So that's the region where it's both bit addressable and byte addressable. So I can say move a byte to location 20 at byte address 20 or byte address 2C, right? That's one of 16 locations. That's easy. Now, at the same time, any one of those 16 locations can also be bit addressable. So if I want to say the fourth bit of byte address 24, how would I do that? Well, so I looked up, okay, for H, it has the bit address 20, 21, 22, 23, 24, 25, 26, 27, right? Because you start numbering the bits from 0, 1, 2, 3, and up, right? So at the byte address 20, those 8 bits have the address 0 through 7. And then at byte 21, those have the bit addresses 8 to 15, and so forth, right? And so you say 24, okay, then 24, a byte address 24. Which bits does it contain? Well, it contains bits at bit address 20, 21, 22, 23, 24, 25, 26, 27 hex. Okay? Let's take a look at another byte. So if you want 2B at byte address, a byte address 2B contains 8 bits. Those 8 bits have the bit address 58, 59, 50A, 50B, 50C, 50D, 50E, 50F, right? Those are 8 bits inside that byte. So as you can see, that means in this region of the memory, there are 2 ways to get to the data. One is either going through its byte address, or the other way is going through its bit address. Okay, there are 2 ways. So that's a special region, and that's why when we talked about stack, and you look at most data sheet, they say be careful not to let your stack go into this region. This is the bit addressable region, because usually the compiler would reserve this region for certain purposes, for the purpose of storing bits, for example, right? Okay, so now there are 16 locations. 16 times 8 is 128. So there are 128 bits, or 128 bit addresses within this 16 byte region. Okay? Now what happens to the other 128 bits? Well, those are mapped to the SFR region. Okay, well this is just an example of reverse calculation. But this part basically says, okay, I have bit address 42. How do I map it back to byte? How do I know which byte and which bit? Oh, so that's a simple exercise. You can try it. So because you have to start from byte address 20. So anything you divide by 8 and then you add to 20 as the start, right? And then the bit part is the same. Okay, so that tells you it's 42 hex of bit address maps to the second bit of byte 28 hex. That's another example. So you can try it later by looking at the slides. Okay, now the other region I was telling you about, because these are the bit addresses 128 or hex 80, right, and up to the last, which is 255 decimal or FF in hex. Those don't map linearly. Those jump by 8 at a time. So we stopped at 7F, right? because that was from bit 0 up to 7F, which is decimal 127. Now, decimal 128 is hex 80, right? So now we have address 80, 81, 82, 83 up to 87. That's 1 byte, and then 88, 89, and to 8 the F, right? That's the next byte, right? Now, so now the first 8 bits map to address 80. The next 8 bits, 88, 89, right? That actually does not map to the byte at 81. It maps to the byte at 88. You see what I'm showing you here? Okay? So that's different from what you saw in the lower region. The lower region was 20, 21, 22 in consecutive bytes. Here, jumps by 8 bytes at a time. And then 90, 91, 92 maps to byte 90. And then bit 98, 99 up to 9F maps to the byte address at 98 hex. Now, so then you can make an observation that, hey, that's interesting, because since there are 8 bits in the byte, by skipping 8 at a time, the starting bit address actually lines up with the byte address. It's identical, right? So that's so let's take a look at so 80 byte 80 contains bit address 80 to 87, and then 88 byte address 88 has bit address 88 also, right? 88 starting. So that's actually convenient because then this mapping is very easy to do, right? So we can take another look, like D8 as byte address. Its bit address starts at D8 also. That's by design. That's not a coincidence. That's by design. So this way, it's actually convenient for the encoding purpose. In other words, if you want to determine a special function bit, you just have to know its special function byte address, and that actually happens to be its bit address, starting bit address also. Okay, that's a detail maybe the programmer doesn't have to know, but I think that's the rationale for designing their or mapping their addresses this way. Okay, so as you can see, the special function registers used, including port 0, P0 at 80, port P1 at 90, P2 at A0, P3 at B0, and so forth. And then 88 is TCON for timer control, and SCON serial control, interrupt enable, and all the other ones. Okay. So now, so this is just to summarize that when you have 80 hex and higher, those are the special function addresses, and the bit addresses are mapped to the same addresses as the byte address, or at least the starting bit address of each byte is the same as its byte address. So that's convenient. And so, right, to calculate the bit address or byte address, it's easy to go back and forth, right? Because port P1.2, or that is the port 1's bit 2, well, you know P1 has byte address 90, so the second bit is 90 plus 2 is 92. That's easy, right? So that's that part.